Here's the first test of the vectors portion of the Calculus and Vectors course. This test is on geometric vectors. I'm going to show you the solutions to this test. Question 1 says, given vectors a, b, and c, construct the following. Well, if I want vector a plus vector c, I need to redraw vector a and c so that they are placed tip to tail with each other. So I've redrawn them, keeping their direction and magnitude the same, but I'm going to place them tip to tail. So I'm going to redraw the tail of c at the tip of a. So I have vector a, vector c. I know the resultant of those two vectors is going to go from the tail of the first vector to the tip of the second vector. So the blue vector is vector a plus vector c. Part B asks me to find vector c minus vector b. So once again, I will redraw vector c and vector b, keeping their magnitudes and directions the same. But when I'm subtracting vectors, I want to place them tail to tail. So I will place the tail of b at the tail of c. Let me label those two vectors. And I know the difference between the two vectors is going to connect the tips of the two vectors. And it's going to go from the tip of the second vector in the pair, so the tip of b, to the tip of c. So it will look like this. This is vector c minus b. The next one. I want to do 2a minus b plus c. Well, for the last one, since I used the method of placing them tail to tail for subtraction, this time I'll do something different. I will do 2a. I'll change it to an addition question. I'll say 2a plus negative b plus c. And now that it's just two additions, I can just place the three vectors all tip to tail with each other, and it'll be easy for me to draw the resultant. So I'm going to need all three of these vectors. I'm going to need vector a, I'm going to need vector c, and I also need negative vector b, which is the opposite of b, which means same magnitude but in the opposite direction. So I need all three of these vectors placed tip to tail. So I'm going to start with 2 times vector a. Well, actually, so I need vector a twice. So I'm going to redraw that vector twice. 2 times vector a is double the magnitude. And then I'm going to that, add negative b. So let me actually move these in a little bit of a different orientation. And then to that, I'm going to add c. Notice I've placed all these vectors tip to tail. So the resultant goes from the tail of the first vector to the tip of the last vector. This is 2a minus b plus c. Right, I've got a plus another a, and then I've got a negative b, and then I've got a c. So there we have it. Let's move on to the next question. It says, write each of the following as a single vector. The first question, part A, says OB plus BF. I can tell based on the way that it's written that these vectors are already tip to tail. The tip of the first vector is at the tail of the second vector. So I know the answer to this is just going to be from the tail of the first vector, which is O, to the tip of the second vector, which is F. But in the diagram, I can see that if I were to add OB and BF, they're already tip to tail. So the resultant goes from tail of the first to tip of the last, OF. Let's do part B. Part B says do vector CE minus CD. When subtracting vectors, it's good if they're placed tail to tail, and I can tell that they already are. They both have their tail at C. Let me draw them in the diagram. I have CE minus CD. When we're subtracting vectors, if they're tail to tail, the resultant goes between the tip of the vectors, and it goes from the tip of the second vector in the pair towards the tip of the first vector in the pair. So it's going to go from the tip of CD towards the tip of CE. So my resultant is the vector DE. Let's do the next one. Part C, we want to do EB plus DC. Let me draw those. I've got EB plus DC. Those ones I can tell are not tip to tail, but when adding vectors, we do want them tip to tail. So I'm going to rewrite those as equivalent vectors that are tip to tail. So I think for this one, what I would do is let's move EB. Let's change that to DA. That's equivalent. And let's change DC to AO. Those two are equivalent. So this question is the same thing as doing DA plus AO. O. And now that those are tip to tail, I know the resultant goes from the tail of the first, D, to the tip of the second, O. So my resultant vector for this one is D, O. Part D, I have GF minus OA. GF minus OA. When subtracting, it's good if they're tail to tail, but these ones are not. So what I think I'm going to do for this one is I'm going to change this to an addition question and then place them tip to tail. So I'm going to change this to GF plus negative OA. Negative OA just means the opposite of OA, which would just be AO. So I'll change it to GF plus AO. So I have GF plus AO, and I want these vectors to be tip to tail. So I'll find a vector that's equivalent to AO but has its tail at the tip of GF. So that would be FB. So this gives me GF plus FB, which is equal to GB. And the last one, I see I've got a mix of adding and subtracting. Once again, why don't we just change this to all adding. So I have FB plus BD. And then instead of subtracting OC, I'll add the opposite. I'll add negative OC, which is CO. And now in the diagram, let me draw those vectors and see what we've got. So I've got FB plus BD. That's good. Those two vectors are already tip to tail. And now I want to add CO. Well, CO is not tip to tail with them, but I could use DA instead. That's equivalent. And now they're all tip to tail with each other. So my resultant vector is going to go from the tail of my first vector, F, to the tip of my last vector, A. So my resultant is going to be FA. Let me just highlight all my answers. And there's that question done. Let's move on to the next one. The next question says, given that EC equals U, so let me draw that in the diagram. EC, so I'm going to put the arrow at C. It says EC is equal to vector U. It says CD, so I'm going to draw the arrow down here for vector CD. CD is equal to vector V. AB is equal to 2 times EC, so AB is equal to 2U. And BC is equal to 3 of vector CD, so it's equal to 3 vector V. So with this information, we want to write each of the following vectors in terms of, it should say U and V. So vector ED, in my diagram, I want ED written in terms of U and V. Well, I can see easily that I can get from E to D by going vector U plus vector V. So my answer to this one is U plus V. Part B, vector BE. That would be this vector here. I want to get from point B to point E. So I'm going to try and choose a path where I know all of the vectors along that path. So I could go 3V and then the opposite of U, so then plus negative U. 3V plus negative U, I'll just write minus U. Part C, I want to do vector AE. So vector AE, that's this vector right here. So once again, I want to get from A to E, so I'll choose a path where I know all of the vectors. I could go 2U plus 3V minus U. 2U plus 3V minus U. And then I should simplify that. 2U minus U is a single U, so I have U plus 3V. dA. That's the last one on this question. dA goes from D all the way to A. Once again, I'm going to choose a path where I know all the vectors along that path. So I'm not going to go this way because I don't know what vector DE is equal to in terms of U and V. So I'm going to go the other way. I'm going to go negative V plus negative 3V plus negative 2U. So this one would equal negative V minus 3V minus 2u. And if I collect these together, I get negative 4v minus 2 times vector u. Let me just highlight all my answers. And there we go. That question's done. Next question. It says vectors a and b are such that the magnitude of a is 10, the magnitude of b is 6, and the angle between them is 40. Now, I have no idea what direction these vectors go in. So I'm going to draw vector a, horizontal, vector b, a little bit shorter than that one. And I know that the angle between these two vectors, that means when they're tail to tail, the angle between them is 40 degrees. Let me also label which vectors these are. This is vector b, which has a magnitude of 6, and this is vector a, which has a magnitude of 10. Part A says, what is the direction of a minus b relative to b? So let me draw a minus b. I know in a difference of two vectors, if the vectors are placed tail to tail, the difference of the two of them connects the tips. And it's going to go from the tip of the second vector to the tip of the first vector. So it's going to go from the tip of b to the tip of a. So it's going to look like that. And I'll label this vector a minus b. And I want the direction of this vector relative to vector b. Before I even worry about finding the direction of it relative to b, I'm not going to be able to find any angles in this triangle until I find the third side of this triangle using cosine law, right? I know two sides and the angle contained by those two sides. So the only thing that we are able to find in this triangle would be the magnitude of the third side. And we would do that using cosine law. So let's find the magnitude of this third side using cosine law. I can say the magnitude of a minus b squared equals 6 squared plus 10 squared minus 2 times 6 times 10 times cosine of the angle contained by those two sides, right? Two sides in a contained angle. Cosine law finds you the third side. So the magnitude of a minus b, after you evaluate the right, don't forget to square root it, and I get about 6.64 units. And now I should be able to find the direction of it, but I want the direction relative to b, so I need to redraw vector a minus b with its tail at the tail of b, so I can find the angle relative to b. Let me redraw vector a minus b, trying to keep its direction and magnitude the same. So there's vector a minus b redrawn. If I want to describe the direction of this relative to b, I need to know what angle does it make with b when they're tail to tail. So I need that whole angle there. Well, I know part of that whole angle is 40. So if I knew this other angle here, let me call it theta, then I would be able to describe the angle between a minus b and b. And notice, based on parallel line theorem, the z pattern, the alternating angles are equal. So I know inside that z pattern, this angle is equal to the angle I want. Now, because I know all three sides of this triangle, I can use cosine law to find that angle. So I would say cosine of theta equals, and when we use cosine law to find an angle, we always start with the side opposite from the angle that we're looking for. So it would be 6 squared minus the squares of the other two sides, 10 squared and 6.64 squared, over negative 2 times those second two sides, 10 and 6.64. I can solve for the angle by doing inverse cosine of whatever that ratio is, and I get 35.52 degrees. Therefore, I can describe the angle between the two vectors as the sum of 40 and theta. So the angle between the vectors is 75.52 degrees. We could write a nice sentence, but I will just put a box around my final answer there. That's the angle that b and a minus b make with each other. Let's move on to part b of this question. It says determine a unit vector in the direction of a plus b. And I have to include a diagram and give an approximate answer rounded to 2 decimal places. Let me redraw vector a and b the way I have them in this diagram. So I think I had the longer vector horizontal, and I had the other one was the shorter one and they made an angle of 40 with each other when they were tail to tail. The shorter one was B, and the longer one was A. It had a magnitude of 10. Now I want a unit vector in the direction of A plus B. Well, first of all, I need to know what does A plus B look like. I'm going to have to find its magnitude, and then shrink its magnitude to 1 to make it a unit vector. So A plus B, if I want to draw A plus B, I need A and B to be tip to tail, but right now, they're tail to tail. So I'm going to have to redraw the tail of B at the tip of A. So I'll redraw vector B, trying to keep its magnitude and direction the exact same. So I tried to redraw vector B here. Its magnitude is still 6, and it's going in the exact same direction. Which means I notice a C pattern here, right? I have two parallel lines connected by vector A. I know angles inside of a C pattern are called co-interior angles, and they add to 180. So I know inside here, this angle here must be 140 degrees. And I know I'm going to want that angle because when I draw vector A plus vector B, I know it goes from the tail of A to the tip of B. So it's going to look like this. And I notice that 140 is inside of this new triangle I've created. So if we look at what I'm highlighting in green, this is the triangle we're now looking at. In that triangle, I'm going to want a unit vector in the direction of A plus B, so I can use this triangle I've highlighted to calculate the magnitude of A plus B. And in that triangle, notice I know two sides and the angle contained by those two sides, so once again, cosine law would find the magnitude of the other side. So the magnitude of A plus B squared equals 10 squared plus 6 squared minus 2 times 10 times 6 times cosine of the contained angle, 140 degrees. Make sure after we evaluate the right side of this, we square root it, and we figure out the approximate value of this is about 15.1. So the length of A plus B is 15.1. If I want a unit vector in the direction of A plus B, I can keep vector A plus B, right? Vector A plus B is that whole vector. It has a direction and a magnitude. I want to keep that direction, but I want to shrink its magnitude to 1. So I do that by multiplying it by 1 over its magnitude, which was 15.1. So 1 over 15.1 times vector A plus vector B. It's the same direction as A plus B, but its magnitude is now 1. And that's what we wanted for that question, is that unit vector in the same direction as A plus B. Question 5. I think question 5 is an easy one. It says that we want to create an expression for the magnitude of the horizontal and vertical components of a force of 10 newtons exerted at an angle of 15 degrees to the horizontal. So I've got some vector that is a force. So I'll call this vector F. And the magnitude of this force is 10 newtons. I want to find the horizontal and vertical components of this vector. So I'm going to break this into its horizontal and vertical components. Sometimes we call these the rectangular components of the vector. Notice they form a 90-degree angle with each other. That's why we call them the rectangular vector components. I know that the force makes an angle of 15 degrees with a horizontal. So with the horizontal component of its own vector, I know it's going to make an angle of 15 degrees. I'm going to label the horizontal component the x component of the force, and I'm going to label the vertical component the y component of the force. And now let's find their magnitudes. Let's find the magnitude of the horizontal component first. And I can always do that because this is the right triangle. I could use SOHCAHTOA, and once you rearrange it, you find out that the horizontal component is just the magnitude of the force times cosine of the angle. And the vertical component is just equal to 10 times sine of the angle. And we can get approximate values for these. The vertical component will be 2.59 newtons, and the horizontal component is 9.66 newtons. So there are my answers for this question. There are only 4 questions left on this test. It says choose only 3 of them, but I'll show you the answers to all 4. These are the application questions. The first question has to do with an airplane. It says an airplane heads out in a direction of south 20 degrees east. So I know I'm going to want to have a Cartesian grid for this so that I can accurately draw these vectors. My first vector, it says it's going south 20 degrees east. So I'm going to draw a vector that's about south 20 east. So I know this is 20 degrees inside of here. And it says that vector is the air velocity vector. So that's what an airplane can do within still air. And it can go 450 kilometers an hour. So let me just label this vector 450 kilometers an hour. Measurements from the ground indicate the airplane has a direction of south 37.5 east with a ground velocity of 398 kilometers per hour. So the ground velocity, which is going to be the resultant of the air velocity and the wind, is going at south 37.5 east. So I know that vector has been pushed a little bit further towards east. So it's going a little bit further. It's going 17.5 degrees further. So I'll try and keep the angle between here 17.5. I can draw that a little bit straighter. So the vector is shorter, and the angle between here is 17.5 degrees. And I think I know the magnitude of this as well, right? It says the ground velocity is 398 kilometers an hour. So 398 kilometers an hour. And what does the question want? It wants, what is the velocity of the wind, the magnitude and direction? Well, I know in my diagram here, I know the blue vector is the air velocity. That's what the plane heads out on a course of. But the red vector is the resultant. So that is the sum of the air velocity, the blue vector, and the wind velocity, which I'm drawing in green here, and I'll label as W. Right? Blue plus green, air velocity plus wind velocity equals the red vector, the ground velocity. That's why I've got the blue and the green placed tip to tail with each other, because I know they add up to the ground velocity. The question wants the magnitude and direction of the green vector, the wind velocity. Well, I can find the magnitude of it pretty easily because I notice in my triangle, I know two sides and the angle contained by those two sides. So once again, I use cosine law. Cosine law would tell me that the magnitude of W squared equals 450 squared plus 398 squared minus 2 times 450 times 398 times cosine of the contained angle, which was 17.5 degrees. If we evaluate that and square root it, we get the magnitude of the wind, which was about 138.9 kilometers an hour. So that's the magnitude of the wind velocity. I also need its direction. Whatever vector I want the direction of, I often like to redraw it so that its tail is at the origin. So I'm going to redraw vector W, trying to keep its magnitude and direction exactly the same. I'm going to redraw it so that its tail is at the origin. And now, if I want the direction of this, I would say that this vector is going north a certain amount of degrees, I'll call it theta, towards east. If I want to find that theta, I'm going to have to use some angle theorems. I always look for equivalent vectors because I know they're parallel. So those are both vector W, so they're parallel, and they're connected by the air velocity vector, the blue one. Angles inside of a C pattern, the co-interior angles, so this whole angle and this whole angle have to add to 180. So if I knew, let me call this angle here beta. If I knew beta, well, actually, let me actually label this part in here as well. I know that part. That part inside of that angle right there would be 90 minus 20 minus 17.5, which is 52.5. So I can label that angle in there 52.5. Right, those three angles inside that quadrant down there are complementary. They add to 90. So if I knew beta, I would be able to calculate this angle right here. Let's call this angle right here alpha. So let's do all that. Let's start by finding beta. Since I know all three sides in this triangle, right, I now know the magnitude of the wind is 138.9 kilometers an hour. Because I know all three sides, I can find an angle using cosine law. Cosine law would tell me that cosine of beta equals the opposite side from beta has to go first, so 398 has to go first. 398 squared minus the squares of the other two. The order of the other two do not matter, so 138.9 squared minus 450 squared over negative 2 times those second two sides. And then I do inverse cos of that whole ratio to figure out angle beta, and I would get 59.5 degrees. So if angle beta is 59.5, now I can figure out angle alpha, right? Because I know that this angle and this angle have to add to 180 because they're co-interior angles inside of a C pattern. So if I do 180 minus 59.5 minus 17.5 minus 52.5, I can get alpha. So alpha would equal 50.5 degrees if I do all of that. And then the last thing I would do is I can now state what theta is. Theta is equal to, well, it's complementary with alpha, so just do 90 minus 50.5, and that gives me 39.5 degrees. So my final answer would be the wind velocity is 138.9 kilometers an hour, and I need the direction. The direction is, if I look up the direction, it is north, theta towards east. So I would say north, 39.5 degrees towards east. Let's do the next application question. A 100 Newton box is held by two cables fastened to a ceiling. So first of all, let me draw a ceiling. And I've got two cables fastened to the ceiling that make angles of 25 and 40 with the ceiling. So I'll make my 25 and my 40 with the ceiling. Let me label those. This looks like the smaller angle, so that's 25, that's 40. And there is a box held by those two cables. I'll put the box right here. And the box weighs 100 newtons. So I know the weight is going to be a force that is going straight down 100 newtons. Determine the tension in each cable. So I know the direction of these tensions is going to be away from the box within each cable. So I have a tension in this cable and a tension in this cable. I'll call those tension 1 and tension 2. Doesn't matter which one is which. I'll call this one tension 1. I'll call this one tension 2. And I know if this box is stationary, I know that tension 1 and tension 2 would add up to the exact opposite of 100 newtons going down. So they would add up to 100 newtons going up so that the box would be not moving. So let me show that in a vector diagram. So in my vector diagram, I'm going to redraw tension 1 and tension 2, trying to keep their magnitudes and directions exactly the same. And I want to show that those two add up to 100 newtons going up. So I've placed them tip to tail to show that they add to 100 newtons going up. And let me label these as my tension 1 and tension 2. And let me actually maybe make this a little bit bigger so we can do some work inside this triangle. All right, so inside this triangle, I'm going to somehow try and place these angles of 25 and 40. Well, I know what angles those make with the ceiling, which is horizontal, so let me draw in some invisible horizontal lines here so that it can help me place those angles. I notice that tension 1 is within this cable, which makes an angle of 25 with a horizontal. So I know that tension 1 with a horizontal makes 25 degrees, so I can label that 25, which means that down here, this is 65, because those two angles would be complementary. And then tension 2 is in that cable, which makes 40 degrees with a horizontal. So tension 2 with a horizontal is 40 degrees. I see a Z pattern here. So I know 40 degrees also goes down here, which means up here is 50 degrees because those are complementary. Now that I have all the angles in this triangle that I have on the right here, I could then solve for the two missing sides because I have the third side. if we have all the angles in a triangle and one of the sides, we can solve for the other two using sine law. So I would say that 100 over sine of the angle opposite from 100, which is this angle here, 65 degrees. So over sine 65 equals the magnitude of tension 1 divided by sine of its opposite angle, which is 50, which equals the magnitude of tension 2 divided by the sine of its opposite angle. Opposite from tension 2 is 65 degrees. Oh, I noticed this triangle is actually an isosceles triangle. Right? This angle right here is 65, and this angle right here is 65. So I know that in this triangle, that side and that side must have the same magnitude. So tension 2 must also be 100 newtons. I mean, if I use my formula that I got here, the sine 65s will cancel out, and tension 2 will just equal 100 algebraically as well. So I know tension 2, its magnitude, is 100 newtons. And tension 1, to solve for tension 1, I would be using this ratio and this ratio. I would get it by doing 100 times sine 50 over sine 65, and I would get 84.52 newtons. There's my final answer. Those are the magnitudes of both of the tensions in the cables. 2 questions left. Question 8. A box with a mass of 10 kilograms rests on a frictionless ramp inclined at an angle of 35 degrees. So I have a ramp inclined at 35 degrees. Let me put 35 degrees in here. There is a box on that ramp, and this time it gives me the mass instead of the weight, so I'd have to multiply the mass, which is 10 kilograms, by 9.8, which gives me a weight of 98 newtons going straight down. Calculate the magnitude of a normal force. Well, I know a normal force is going to act perpendicular to the surface. So I'm going to draw my normal force here. That's pushing back against the box, keeping it from coming down through the ramp. And a force applied at an angle of 20 degrees to the ramp that would keep the box at rest. So there is some other force, not friction, some other force, right? This ramp is frictionless. Some other force applied at an angle of 20 degrees to the ramp that is keeping the box at rest. So the sum of the normal force, let me redraw it. Here's the normal force. The sum of the normal force and the other force that's at 20 degrees to the ramp. So let me draw these tip to tail. Here's the other force. The sum of those two are keeping the box at rest, which means they add up to the opposite of 98 newtons down, which would be 98 newtons up. We just have to now figure out how can we place the angles that I have in the question into this triangle so that I could solve for the magnitudes of those two forces. So once again, let me start by drawing in this horizontal line here. And then let's figure out this force, vector F, what angle does it make with a horizontal line? Well, hopefully you can see that if I redrew vector F, that force with its tail down here, what it makes with a horizontal line is the sum of 20 and 35. So in my diagram over here, I could make a 55-degree angle right there. The other thing I need to notice is that the normal force with force F makes an angle of 90 plus 20. So the tip of the normal force with the tail of the other force makes an angle of 90 plus 20, which is 110. So this whole thing here has to be 110. Which means this other angle right here also has to be 55. And now I can just use triangle properties to find the other two angles, both of them to be 35 degrees. Once again, for this question, I've got an isosceles triangle. So after I solve for one of the magnitudes of these forces, the other one's going to be the same. Because this angle and this angle are the same, I know that their corresponding sides are going to be equivalent magnitudes as well. So I could use sine law to solve for this, using that big triangle that I have here, highlighted in yellow now. Sine law would tell me that each side, so for example 98 over sine of its opposite angle, which is 110 degrees, right, this whole angle is 110, is equal to the magnitude of the force divided by sine of its opposite angle, 35, which is equal to the magnitude of the normal force over sine of its opposite angle, 35. So the magnitude of the force is equal to the magnitude of the normal force. And they're both equal to 98 times sine 35 over sine 110. And that would be equal to 59.82 newtons, approximately. Let's move on to the last question of the test. It says John wants to canoe across to the other side of a 40-meter wide river. The river is flowing at a rate of 10 meters per minute, and John can paddle at 25 meters per minute. I assume that means in still water. In what direction should he aim the canoe in order to land at a point directly opposite of his starting point? So first of all, let's draw the banks of a river. So I've got some river, and it tells me that he wants to land directly across from his starting point. So let's say he starts right here. Start. He wants to finish directly across here. So he wants this vector, the one that goes from here to there, he wants that to be the resultant of the two vectors that I'm going to place in the diagram. That needs to be the resultant. The other two vectors that are going to go into this diagram are the vector that describes how the river is flowing and also how John can paddle within still water. So John can paddle at 25 meters per minute in still water. So he's going to need to go out at some angle to the bank. I'll call this angle theta. Or we could find what angle upstream he needs to paddle at. I could call that theta. It doesn't matter. But I know he's going to go at some angle so that the current, let's just say the current flows this way. The current is going to push him back so that he lands directly across the river from where he started. So in this diagram, this is what John can do in still water, but the water is actually flowing at 10 meters per minute. And we just picked that direction that it's flowing. It could have been the other way. And I know that the sum of those two vectors has to be going straight across the river. The first part of this question says, in what direction should he aim the canoe? So let's solve for theta. Notice this is a right angle triangle. Right here is a 90-degree angle. So to solve for that angle, from angle theta, I know the opposite side and the hypotenuse, so I would use sine. I would say sine of theta equals the opposite side, 10, over the hypotenuse, 25. So angle theta, I would get just by doing arc sine or inverse sine of 10 over 25, which is 23.58 degrees. And now I don't know exactly the direction as like a quadrant bearing, so I don't know what direction this river is flowing or anything like that. So I would just say that amount of degrees upstream. That's the angle that he has to head out at so that he lands directly across. The next part of the question says, how long will it take him to cross this crossing? Well, I know the distance to get across the river is 40 meters. And it says how long, so I'm solving for a time. Well, I know that velocity equals distance over time. So if I'm solving for time, I know time equals distance over velocity. Well, I know the distance he has to go is 40 meters directly across the river. Well, at what speed is he going to be going across the river in that direction? So I'm going to have to figure out what is the magnitude of my resultant vector here. That's going to tell me what his resultant velocity is that is going straight across the river. So I'll solve for that. I could just solve for that using Pythagorean theorem if I wanted to. In that right triangle that I have, I could say that the magnitude of r, I'll do that here, the magnitude of r squared equals 25 squared minus 10 squared. So the magnitude of r is about 22.9 meters per minute. So the current is actually making him go a little bit slower than he's capable of doing. So when I calculate my time, I will do the distance, 40 meters, divided by his resultant velocity of 22.9 meters per minute. When I divide these two, I get about 1.75 minutes. That's how long it's going to take him to go directly across the river. So let me highlight my answers. He's got to go 23.58 degrees upstream, and it's going to take him 1.75 minutes to get across the river. There you go. That's the end of the test. Jensen Math!